Hi, welcome to ERC Tipsnology. This is actually the continuation of our discussion about writing a program in 8051 microcontrollers using timer delay. So this is part two of that series. So the following again are the characteristics and operation of mode 1. So first, it is a 16-bit timer. Therefore, it allows the value of 0000 to FFFF to be loaded into the timer's register TL and TH. First, this four zeros is actually 16 zeros in binary. And this four Fs, FFFF in hexa is actually 1111 four times or 16 ones in binary. So don't think that this 000 means 4 bits. It's actually 16 bits. And FFFF is also 16 bits if you converted it to binary. Now the TL here means the low byte of the timer, and TH here means the high byte of the timer. If you watch the part one of this tutorial series about programming timers, then you will know what I'm talking about: the low byte and the high byte. Again, uh, each timer, whether timer 0 or timer 1, is 16 bits wide. And the 16 bits wide is divided into two parts: 8 bits for TL or the low byte of the timer, and 8 bits for the TH or the high byte of the timer. That's what we mean by TL and TH. But of course, you need to write the timer number 0 or the timer number 1. So whenever you write TL, we need to write it as TL0 or TL1 or TH0 or TH1. But here, generally speaking about timers register, we don't need to write the number. So that's number 1. So we're talking about the characteristics of mode 1, operations of mode 1. For number 2, so again, for number 1, it is a 16-bit timer. Therefore, we can count, or it will allow 0000 to FFFF to be loaded into this timer's registers. Now, after the TH and TL are loaded with a 16-bit initial value, again, this initial value will still need to be calculated so that we will determine what numbers in hexa will we put on the TH and the TL. So the timer must be also started. And to start the timer in C language, we just write TR0 equals 1. Or if you're using timer 1, TR1 equals 1. You see, by putting 1 in our timer timer TR0, it will be starting to run. Now in assembly, if you want to make TR0 as 1, the command is set B TR0. This is for timer 0 to run it. And if it is timer 1, then the command is set B TR1 for timer 1. Again, TR0 equals 1 semicolon, or TR1 equals 1 semicolon. This is for C language. For assembly language, set B TR0 or set B TR1. No need to put the semicolon. Now, after the timer started, then it will start to count up. So as I've said, it will start counting from 0 up to FFFF, or whatever is the value where this timer will start from. It will count up until it reaches its limit of FFFF. So if you set on what particular number will the timer start, then it will start from that number until it reaches FFFF. Now, this is represented here by the block diagram. This is the crystal oscillator. And you have here the block that says divided by 12. And you have the C or CT equal to 0. So this will operate as a timer. And what will happen is it will start to run. and the TF will go to high, for example. The TF is the flag of the timer. So TF, while the TF is equal to 0, then we will be just continue to count up. But when the TF becomes 1 or it goes high, this will be happening when you already reach the uh, uh, the last number for your counting up. And what will happen is there will be another addition of 1 to this FFFF. So what will happen if you add FFFF plus 1 more count? Of course, it will go back to 0. So it will be what we call as roll over, or it will go back to 0. And that's a signal that we are done counting, or we are done with our timing. And when that happens, the timer flag will automatically be equal to 1. And so because of that, we need to do the next part, which is to when it rolls over from FFFF to 0, then we need to set the flag bit called the timer flag. We need to make it equal to 1, or we don't need to make it. It will be done by the computer itself or the program itself. Again, when it rolls over from FFFF to 0, this means that you already reached the maximum value of your timer, and there's no other number where it will go, because we cannot have it as 10000. I mean, FFFF is the last. So if you still count up or add the time to it, then it will go back to 0. And that will automatically set the timer flag TF, whether it's TF0 or TF1, to be equal to 1. And each timer has its own timer flag. Again, we have two timers, timer 0 and timer 1. So if you want to say talk about timer flag of timer 0, then we say TF0. And if you're talking about the timer flag of timer 1, then it will be TF1. Now, this timer flag can be monitored in your program. You just need to check if it is C language, like something like while, open bracket or open parenthesis, TF0 is equal to 0, close bracket, semicolon. So in this case, it will do nothing while the timer flag of timer 0 is equal to 0. Whereas if it becomes 1 automatically, then it will stop doing nothing and it will move to the next line, which is to make the timer to stop and the timer flag back to 0. I will show you that to you when we write the program. Now, when this timer flag is raised, it means that the TF, whether TF0 or TF1 equals 1, or TF0 equals 1, one option would be to stop the timer. And to do that, you can just write in C language TR0 equals 0 if it is timer 0. If it is a timer 1, then TR1 equals 0. I will just show you that to you again later on. And if it is assembly language, the command is CLRTR0 if it is timer 0 that you want to stop, or CLRTR1 if it is the timer 1 that you want to stop. Now, number 4, after the timer reaches its limit and rolls over, meaning that you already reach FFFF, there's no other number to go, so it will go back to 0000. That's what we call rollover. It will be able to repeat the process again. So TH and TL must be reloaded with the original value, and whatever that's the original value is, and the TF must be reloaded to 0, so that it will mean that the TF flag, or the timer flag, is equal to 0. It means that it's done with its timing, or with counting up. So as you can see here, the crystal oscillator, here CT equals 0, this is a timer, and it will start counting up. and the TF will goes to high whenever the FFF becomes 0. So this means that when you reach the maximum number FFFF and it goes back to 0, the timer flag will become high automatically. You don't need to put it in your program that you will make it TF equals to 1. All you have to do is to monitor it by using while TF1 or TF0 is equal to 0, close bracket, semicolon, do nothing. I will show you that in the program later on. And then the timer flag must be again set to 0 or goes back to 0 when you are done counting up. So this is the overflow flag again. Now, to generate a time delay, what are the steps? This is for mode 1 program. First, we load the T mode value register indicating which timer, whether timer 0 or timer 1, is to be used and which timer mode 0 or 1 is selected. If you don't understand this in C language, we will just put TMOD equals 0x 01. If it is timer 1, mode 0, timer 0, mode 1. So again, I'll repeat. Tmod 0x, tmod equals 0x 01. This means you are using timer 0, mode 1, or timer 1, mode 0. Now, I will explain this more later on, but again, the T mode, in other words, for number 1, determines whether you're using timer 0 or using timer 1 or you're using mode 0, mode 1, mode 2, or mode 3. For number 2, we load the registers TL and TH with initial count value. But of course, we cannot just put any number on TL or th. We need to calculate the value of these initial values for determining up to how much millisecond or microseconds or second your timer will be delayed. So we need to have some calculations for that. And the third step is to start the timer. Of course, we can do that by sending one or giving one to our TR. So in C language, what we do is TR equals 1 semicolon. Now, by the way, for number 2, if you are using timer 0, you have to put TL0 equals 0x and then your hexadecimal number. And TH0 equals 0x followed by your hexadecimal number. Now, if you're using timer 1, it must be TL0 equals 0x followed by the hexadecimal number that you calculated for the initial values, and the th1 equals 0x followed by the hexadecimal number that represents the initial value that you will calculate later on. I will show that to you too. Now, on the number 4, we will keep monitoring the timer flag with the JNB uh, TEX target instruction so that we will know whether the uh, the timer flag is already done. Not T not TFX, I mean T not TEX but TFX. Now, this TFX means timer flag for 0 or timer flag for 1. So this is TF0 or TF1. And then in C language, we use while to check or monitor the value of the timer flag. Again, if the timer flag is still 0, it means that the timer is not yet done. And if the timer flag is it becomes 1, then the timer is done counting and there will be a rollover. And it will get out of the loop when the timer flags becomes high. And number 5, we stop the timer. So to stop the timer in C language, we just put uh, TR0 equals 0 or TR1 equals 1. If it is assembly, we will be using the clear statement here like this: CLR TR0 or CLR TR1. Now, the last step or second to the last is the we clear the TF flag for the next round. And to do that in C language, it's only TF 0 equals 0 if it is timer 1, or TF 1 equals 0 if it is timer 1. So timer 0. So TF 0 equals 0 for timer 0, and TF 1 equals 0 for timer 1. And the last one is to go back to step 2. We will load the registers TL and TH again with the initial count value again and again until it continuously run. Now, let's see this example 9-4. In the following program, we will create a square wave of 50% duty cycle. This 50% duty cycle means that it will have equal parts or portion for the high signal and the low signal. And this will be done on P1.5 bit. And here we will be using timer 0 to generate the time delay, but the mode was not mentioned, whether we will use mode 0, mode 1, or mode 2, or mode 3 in the problem. Therefore, we can use whatever mode we want from the four: mode 0, mode 1, mode 2, or mode 3. Now, usually we use mode 1. So in this example, as you can see on the comment here, for assembly, we use semicolon for the comment. So timer 0, comma, mode 1, this is for the 16-bit mode. If you don't remember it, we can go back to the 16-bit mode here. You will see here that when the M1, M0 is 01, we are using mode 1, and this is 16 bits. So going back to this example that we are talking about, the mode 1 is 16-bit mode, and we will be using timer 0, although we can also use timer 1, but in this problem, timer 0 is being asked. So the first line says move TMOD, comma, #01. What does it mean? It means that the timer mode will have a value of 0000, that is representing the 0, and the 0001, that is representing the number 1. Again, in the 0000, the gate is 0, CT is 0, and the mode M1, M0 is 00. And for the number 1, again, this is hexa 1. In binary, that's actually 0001. So the first 0 represents the gate, the second 0 represents CT, and the last two numbers 01 represents the mode. And because that's 01, then it will be mode 1. If you still don't understand, we can go back to the table here. 0000, that's timer 1, mode 0. 0001, that's timer 0, mode 1, because this is 01, and 01 is mode 1. So again, 0000, timer 1, mode 0. 0001, timer 0, mode 1. So that's it. But of course, in the example here, we don't really write 0000 or 0001. It's up to you to represent it in your mind that these are hexa values. Okay, and it's not really binary. So just don't forget that we are talking about binary and hexa here. Like this one, this is binary. Tmod equals 0000001. This is okay. This is binary. But when you say tmod equals #12h, then the h here represents hexadecimal. Actually, the example we are talking about here, I think they missed writing h here. So let's just say that this is hexa. Now on the next line, you will see the word here and then colon. So colon. So here colon, it means this is a label that represents something or a place where we will go back. As you can see here, we have SJMP here. SJMP here. When you reach this line, it means you will go back to here, this label, and you will repeat 1, 2, 3, 4, 5. Go back 1, 2, 3. That will be a loop. So in the second line, we move F2 or 0F2H to our TL0. You will notice that whenever there's a letter in the beginning of the value, like here, we are supposed to only put F2 in assembly. This might be taken into a wrong meaning. It can be a variable because it starts with a letter. Therefore, the rule here is every time you want to put a hexadecimal number to TL0, you need to put a 0 before the letter F. That's a requirement. So hashtag 0F2H actually means F2. So TL0 will have a value of F2. Again, F rep is it means 1111, and 2 means 0010. So we are actually putting 1111 to TL0, or the low byte of timer 0. Now on the third line, we are moving FF to the high byte of timer 0, which is TH0. So we have here, actually the comment here is that TH0 will be equal to FFH, or to the high byte. In other words, the number here is like from 2, and the number here is F. So F2, and the highest is high byte is FF. And then what we will do is we will get the P1.5 and make it 0, and then 1 when it goes back. This is to toggle the port 1.5. We will use the CPL command. Okay, so that's how it is. And then we have here something like a call delay. So it means it will call a delay function, and in this example, the delay function was not shown in this step. But basically, this delay will be giving a delay to our toggling of P1.5. So to continue, how to find the loaded timer values. To calculate the values to be loaded into TL and TH registers, we look at the following example. Assume that the crystal is 11.0592 megahertz. We can use the following steps for finding the TH and TL registers values. So first, we need to divide the time delay by 1.085 microsecond. That's a constant value that we got from dividing 12 by 11.0592 megahertz. Again, where we got the 1.085 microsecond, we divided 12 by 11.0592 megahertz. So again, going back to what I'm telling you, we need to divide the desired time delay by 1.085 microseconds. So the time delay may be in second, or a millisecond, or microsecond, or nanosecond, but you have to make sure that before you divide the time delay by 1.085 microsecond, they must be in the same unit. So the time delay must be expressed in microseconds so that you can divide it by 1.085. For example, if you want 1 second delay, then you cannot put 1 second divided by 1.085. You need to make 1 second to become microsecond. So what is 1 second in microseconds? That will be 1 million microseconds divided by 1.085. Another thing to consider is that when you subtract this value from our constant, like in number 2, we're supposed to perform 65,536 minus the number that you calculated. The answer must be positive number. If the answer is a negative number, then you cannot go to the third step. That's one important thing. What I mean, for example, if simply write 1 million divided by 1.1 million microsecond to represent 1 second, divided by 1.085 microseconds, of course, the answer there would be a little less than 1 million, and let's say 999,000 something. But when you subtract that to from 65,536, then the answer would be 65,000 minus 900,000 something. Then the answer would be negative, right? So you cannot use 1 million divided by 1.085 microsecond. So the solution to this is you have to come up with another time delay. For example, I want 1 second, but I cannot use 1 million microseconds. So I'll just be using maybe 10,000 microsecond so that I can divide it by 1.085, and my answer would be a little less than 10,000. So what I mean is when I subtract 65,000 something minus uh, almost 10,000, the answer will not be negative. But my problem now is I changed the 1 million microseconds to 10,000 microseconds only. So it will not be the solution to the question. So if we want 1 second, again, we cannot make it 1 million microsecond divided by 1.085. So what I'll do is I'll simply use 10,000 microseconds. And then when I got the answer, I can uh, multiply that answer by, so let's say whatever is the answer to represent the 10,000 microseconds, then we can multiply it by 10,000 multiply by something to make it 1 million, and that something could be the 100. So 10,000 multiply by 100, that will be 1 million. So in our program, I'll show you later on that the 8051 timer delay that we used will be repeatedly called 100 times in order to get the 1 second. Right now, it's still not clear, but later on, you will see that. Now, on step number 3, we will convert the result of step 2 to hexadecimal number. Again, it will just be done if the answer in step number 2 is positive. And the hexadecimal number will be represented as the first two digits, let's say YY, will represent the TH, and the second two digit XX will represent TL. That's how you get the TL and TH values of the registers when you are asked to calculate for the initial values of these low byte and high byte registers. Again, this is still in the theory part. You will see this later on when we write the program. Now, moving on to the next part, we have here another example, 9-10, that assumes that xtal is equal to 11.0592. And the question is, what value do we need to load the timer's register if we want to have a time delay of 5 milliseconds? Show the program for timer 0 to create a pulse width of 5 milliseconds on P2.3. Just to make this more easy for you to understand, we are supposed to create a pulse for pin 2.3. When you say pulse 0 and 1, we can also say toggle, or we can say blink if it is an LED. And this is like the P2.3 will have a value of 0 every 5 millisecond, and a value of 1 every 5 milliseconds. And the problem is, what is the 5 milliseconds for timer 0? Let's say mode 1. So the mode 1 was not given here, but let's say we will use mode 1. Again, the mode 1 for timer 0 will be using 1.085 microseconds if your crystal is 11.0592. So to get the TH and TL values as given in the formula here, we subtract 65,536 minus the delay divided by 1.085. So the delay is supposed to be 5 milliseconds. So we cannot divide 5 milliseconds by 1.085. Therefore, we will convert 5 milliseconds to 5,000 microseconds so that we can divide it. So when you divide 5,000 microseconds by 1.085 microseconds, then you will get an answer, and we will subtract it from 65,536. Like here, the answer on 5,000 microsecond divided by 1.085 microsecond is equal to 4608, and this is already rounded. And then you subtract it from 65,536, and you will get an answer in decimal, of course, but in this example, it's already converted to EE08. So we will just continue on part 3 for this discussion.